Hello, everyone. My name is David Gerustondo. I'm a professor on environmental technologies. Well, I'm going to talk about air pollution, effects on health and public health. I'm not a toxicologist. I am a rare avis here. And my field of work is focused on environmental pollution in general. Today, I will talk about air pollution and the effects on ecosystems and health. But my work finished to determine the exposure. Okay. Well, then the first two slides are a bit of an overview, a brief overview. So why is this atmospheric chemistry important? Because we live on the troposphere. So we are breathing this air. The atmosphere is a huge reactor. A huge reactor where there are a lot of components that react among each other. Okay, these atmospheric pollutants impact living organisms, impact ecosystems, so affects vegetation, plants and fauna, biodiversity in general. They also affect climate change, and obviously, and that's why I'm here today, they affect health, human health. Well, these atmospheric pollutants are responsible for most of the environmental issues we have today. We talk about acid rain or smoke processes that are directly linked to air quality, or the stratospheric ozone hole, or the climate change. All of them has a characteristic, and they initially start by emissions of pollutants to the atmosphere. And finally, the regulatory policy requires a complete understanding of pollutant impact. Okay, there are briefly how to classify pollutants. So there are two types of pollutants: primary pollutants that's directly emitted by the exhaust, for example, in traffic, or secondary pollutants, those formed in the atmosphere by chemical reactions. Ozone, for example, is a secondary pollutant. Ozone has never emitted directly from exhaust or tags. But apart from ozone, that is the most famous, there are other like part of the particulate matter or even NO2, nitrogen dioxide. These three pollutants are essential at the when it comes to understanding the effect on health of this pollutant. So, well, we have these primary pollutants directly emitted by the exhaust, for example. In case of nitrogen oxides, is nearly all is emitted as nitric oxide, and this nitric oxide immediately starts to react to give nitrogen dioxide. At the same time, ozone is formed, and particulate matter can come from these gases to form this particulate matter. It means that they will affect not only locally, but regionally. Okay, according to the source, they can be biogenic or anthropogenic. So it's very clear that the anthropogenic means, but some of these pollutants can be also biogenic. For example, Sahara-Sahara intrusion of particulate matter, or volatile organic compounds emitted by forests, or pollen. Pollen is considered a pollutant, and it's especially interesting today because there are interesting interaction between pollen, climate change, and air quality. And according to the species scales of their effect, they can be local, or micro scale, regional or macro scale, and global. Okay, well. Talking about these pollutants, I like to distinguish between different pollutants according to the effect of these pollutants. Okay, CO2 and carbon monoxide are emitted to the atmosphere in the same way. Both are considered pollutants, but the effect is totally different. In terms of air quality, it means the effect on health. We have the carbon monoxide, nitrogen oxides, tropospheric ozone, particulate matter, and sulfur compounds, especially SO2. This we'll talk about then during this presentation because these are they are subjected to regulation in Europe and all around the world. But apart from this, and the problem of these gases, they produce a direct effect. They have a direct effect on health. Apart from them, there are other heavy metals, cadmium, copper, or polycyclic aromatic hydrocarbons. The most interesting in terms of quality is benzoylpurine. Again, they are gases or metals. They are toxic, directly toxic, or carcinogenic, teratogenic, mutagenic. Okay. Then we have another one like ammonia. Ammonia is toxic on their own, on its own, but in terms of air quality, it's especially important because not only because, or not as much as the direct toxicity of ammonia, because they must reach very high contents, but for the effect in the formation of particulate matter, PM2.5. Okay, so PM2.5, I will explain to you that is the most dangerous pollutant in terms of air quality, and ammonia, with the reaction between ammonia and nitric acid or sulfuric acid, can produce this PM2.5. And there are also persistent organic today like pesticides. Some emerging pollutants can be considered. Today in other talks has explained something about these persistent organic pollutants, and they have a direct effect, a direct toxic effect on health. But apart from these gases, there are other gases like carbon dioxide, methane, or nitrous oxide. They are greenhouse gases, but they don't have a direct effect on health. They will have an indirect effect on health because of the change of the climate patterns and all the problems directly related to climate change and global warming. And we have also CFCs that are related to the stratospheric ozone depletion. And again, they don't have a direct effect on health, but they will cause the ozone depletion because of the reaction with ultraviolet light in the atmosphere. And then this toxicity or the scale of the effect is related to reactivity. In this case, for example, we have the long resident time species are the CFCs or the greenhouse gases. They don't have an effect, a direct effect on health, but they have an effect on climate change or this ozone, and it's because of the low reactivity. That's why they don't react, and they can remain for a long time in the atmosphere. That's why they have all this process. Here we have the medium resident time species or the air pollutants. This air pollutant with that affect our health will be here. So ozone, nitrogen oxides, particulate matter, and then they have a medium resident time species. They tend to react. They are reactive, and then it means that they will disappear by reaction in the atmosphere. But in this case, well, they are considered medium resident time species, and there are some resident time species like free radicals that are the starting point of the reaction in the atmosphere, and the volatile organic compounds that tend to react nearly immediately. So okay. So here today we'll focus especially in this medium resident time species, in this mesoscale. It means that here we have the global problems. It means that a greenhouse gas that is emitted here will affect the whole planet. And here we have local or regional processes. It means that it will affect only this area. However, there are so many urban areas in the world that at the end it's a global problem, but the scale is local. Okay? Well, and then, okay, that's more or less a bit of context for you. And then what is happening with air pollution? Why I consider the air pollution is important? Because I think that often has been overlooked. Air pollution is one of the main environmental risk factors associated to premature deaths. According to World Health Organization report, every year 4.2 million premature deaths are caused by air pollution. To give you a bit of context, during the COVID, in 2020, in the first year after the COVID, the number of deaths, the COVID was the most catastrophic event in terms of health in the last 100 years. Okay, the number of deaths was 1.8 million, but taking into account the huge uncertainty to these estimations, it's the WHO says that measuring the global excess mortality, the first year, in 2020, the number of deaths due to COVID was about 3.4 million. The most catastrophic event in the last 100 years. And every year, there are more deaths directly linked to air pollution than in this case, for example. Okay, here we have 4.2. And equally distributed throughout the world, especially important in poor countries or in Eastern Asia or Africa countries. But anyway, it's 7% of total death. More or less, there are 60 million deaths in the world yearly, so it's a 7%. If we add the indoor air pollution, for example, today, I think Hellas has talked about the indoor air pollution, we're talking about an 11% of the total deaths in the world every year are caused by air pollution. Well, here we have the global attributable deaths. It's a paper of 2020 of the Lancet. And here we can see that it's true. The air pollution is the fourth cause of deaths, both in male and female. Of these deaths, 60% are caused by cardiovascular diseases. More or less at 20-25% by respiratory illnesses, and then there are other diseases, other illnesses like cancer, lung cancer, bladder cancer, or diabetes, or something like this. Okay, so but this is the fourth cause of death in the world. But apart from these problems with mortality and obviously the link problems with morbidity, there are another problem that is the cost. Here we have three reports. This is the OECD that is established that the cost of outdoor pollution is about 3 trillion, and here the global cost is the World Bank report that takes that more or less 10% of the GDP, the total GDP in the world, is spent to avoid air pollution, health problems linked to air pollution. Okay. And this is the last report. This report is from the European Commission, and this linked to the new proposal of air quality directive. I'm going to explain now. And they estimate that will be necessary 6 billion per year in order to decrease the PM 2.5 in order to reach the new values. But anyway, the benefit will be more than 4 billion years. So for each $1 or €1 will obtain 6 or more euros, avoiding health problems, avoiding lot of work hours, and so on. Okay, then it's clear that something happened with air pollution because it's the fourth cause of death. More than 4 million people die every year. And okay, which are these effects? Okay, obviously depending on the concentration of pollutants. In low concentration or chronic concentration, there are problems or acute concentration, sorry, irritation, cataracts, headache, and fatigue, or diabetes, or respiratory diseases. Obviously linked to it, here exacerbation of asthma, or pulmonary edema, or chronic obstructive pulmonary disease, similar to tobacco, for example. Okay. And obviously cardiovascular diseases, say 60% of death are caused by cardiovascular diseases, especially stroke and ischemic heart diseases, and obviously lung cancer, because the outdoor air pollutant and particulate matter were classified as carcinogenic from the group 1 by the IARC. Okay? But this, that is the typical problems. There are other effects that are not considered as illnesses, and there are plenty of studies. Here I give only one example. It is a study carried out by Sriyer and colleagues in schools located near or far from polluted areas, and they studied the cognitive development in children. And here the results were very significant. There is a significant decrease in the cognitive development of these children, of children that are in a school located nearby or close to this traffic or these high emission points. Okay, so it's not an illness, but anyway, something similar similar studies. There are similar studies with heavy metals and with many other things that affecting specifically the cognitive development. Okay, then not all the people are affected in the same way. Obviously, there will be professions that will suffer more because they are working in urban places, on the streets, but especially there's a division due to the sensitivity. There are sensitive groups, mainly people with pre-existing health conditions, from cardiovascular, respiratory problems, and obviously young children because of the size of the respiratory system, and the elderly. Okay, so it's impossible to avoid these pollutants because we have to breathe. So we breathe from 6 to 8 liters per minute, but we have natural protection against these pollutants, mainly linked to the nose hairs or that feel the particles, or a cough or sneeze, or bronchial constriction, or macrophages, etc., etc. But the problem is when the pollutant can enter the body, and when it enters the body, it can be deposited in urine, blood, soft tissues, or bones, depending on the type of pollutant. Okay, the behavior of the pollutant, the capacity of this pollutant to enter the body will depend in gases of the solubility and in particles of the shape and size. I'm going to talk about it. Okay, in gaseous pollutants, the capacity of penetration of these pollutants will depend on solubility. It means that when the pollutant, this gas, is highly soluble, then it won't penetrate. It will remain in the upper part of the respiratory system. The problem is when these pollutants enter the alveoli, enter the lungs. So, for example, SO2 or ammonia has a high solubility. That's why they cannot penetrate, and that's why they are less dangerous than, for example, NO2 or ozone, NO2 that is whose solubility is very low and then can penetrate in the inner part. Okay? And with particulate matter, I'm going to use two slides to explain that a particulate matter is. Everyone knows has heard about particulate matter, but I don't know if you really know who is a particulate matter. Particulate matter or particles is a mixture of solid particles and liquid droplets. Some of them are emitted directly or are natural. For example, the Sahara-Sahel intrusions that are sand from the Sahara-Sahel. That is very common in Europe and even in Scandinavia in the last years due to the climate change. But there are also secondary particles that are produced in the exact place when they are emitted. It means that depending on the pollution of the place, the concentration, the chemical composition of these particles will be different. And it's important because particulate matter is divided in different sizes, in the diameter of the particle. Particles with more than 10 micrometers are called sedimentary particles, and they cannot penetrate our barriers or our protective systems, like in the nose, in our throat, and so on. We talk about particulate matter when the diameter is lower than 10 micrometers. In this case, from 10 to 2.5 micrometers are called coarse particles. Look at the size. This is a human hair, and this is a fine beach sand. And here we have the 10 micrometers that can be dust or pollen or mold. Then we have the 2.5 micrometers that are combustion particles, normally secondary, that can penetrate much more. We'll see in the next slide. Or we have nanoparticles or ultrafine particles with minus than 0.1 micrometers that behave exactly the same as a gas. These ultrafine particles are especially important in the last directive. Okay, then this particulate matter can penetrate, can stay here, remains here, can penetrate the trachea or the or bronchiolo, and or the respirable minus 2.5 micrometers or 4 micrometers can penetrate the lung and the alveoli. Okay, it's important because particulate matter has two effects. The first one is the physical effect. Okay, you are breathing a particulate matter, a dust, so it produces an effect. It doesn't matter if it's natural or not. But apart from this physical impact, it will have a chemical damage that will be directly linked with the chemical composition of this compound. That's why it's important when this particulate matter has been produced. It won't be the same if this secondary material in a rural place, for example, that in an area, in a urban and industrial area with dioxins, polycyclic aromatic hydrocarbon that can absorb in this particle, or radioisotopes. Because when you have ultrafine particles that can penetrate without any problem, then with alveoli, in the alveoli we have a cell layer, and then they can penetrate to the blood, and then this following the blood they can end in the brain or the kidney or liver, and then they can emit the pollen. In the radioactive, we have polonium, for example, the radiation can be emitted directly in the brain. Or we have mercury or cadmium, it will affect directly the organ. That's why the size and the composition of this particular matter is so important. And it explains why, when I talk about 4.2 million people that die, nearly 80% is due to particulate matter, specifically PM 2.5 or less. Okay? Then it's obvious that we have a problem, and then what to do? Then, well, the WHO create air quality guidelines. This is in 2005, and this is the last version in 2021, and they create these values, the guidelines. These are the science-based concentrations over which there will be an effect on health. With time, in the last 60 years, there have been a lot of studies, a lot of papers that have discovered that the previous values were too high. That's why today the guidelines are more or less half. Okay, for example, PM 2.5 or PM 10 and so on. Okay, what's happening in Europe? In Europe, there have been a significant reduction of emissions in recent decades. Here we have an unequal reduction. For example, for SO2, the reduction has been higher than 70%. But for example, ammonia remains more or less the same. Or this decrease has been negligible. That's why ammonia is a big problem today because of not only because of the effect on health, but many other effects. But there are others like PM 2.5 that has decreased less than 20%, or sorry, here. Okay, or okay, there have been a reduction. And this reduction is due to the European regulation. The European regulation, especially linked to the Clean Air Directive or the National Emission Savings Directive, apart from sectoral regulation. In Europe, the regulation works, for example, the Water Framework Directive gives an objective, and then under this umbrella, there's a lot of regulation in order to obtain this objective. Okay, here there was a mother directive in 1999, and from this there was some daughters directive, and finally today we have this directive, the 2008-50 on ambient air quality and clean air in Europe. in order to control or to ensure that the air we breathe is under these values, under this threshold. And then when the concentration exceeds these limits, then the government or administration has to take measures. That's why, for example, in Brussels or Madrid and Barcelona, it's typical to find problems when the emission or the concentration of these pollutants increased. But apart from it, there is another directive that is the National Emission Ceiling Directive. This one, on the reduction of national emission ceilings of certain atmospheric pollutants. The idea is to decrease the amount of pollutants emitted in Europe. Each country will have less and less pollutants in order to avoid effects on ecosystems and obviously also on health. Okay, then we know that there has been a decrease, and then these are the results of the last report. On the left, we have the people breathing air exceeding the limits of the air quality standard, air quality directive in the European Union. So it means that less than 20% of us are breathing MAF, air quality air. Okay? But according to the guidance of the world of the WHO, so it means that all of us are breathing air over the limits. The WHO limits are the science-based limits, but there is no coincidence with the regulatory limits. Then, in the same report, we have these values. These are the number of deaths of the last year in Europe. Okay? So they're exceeding 300,000 in the European Union, 300,000. It seems difficult to understand that if only 20% of us are breathing air under the limits, how is it possible that more than 300,000 people die? Okay. Well, this is why there's no coincidence between the WHO limits and the directive limits. Okay, the Ambient Air Quality Directive, the 2008-50, is focused on these pollutants, the main pollutant, the pollutant I have explained before that are producing a direct effect on health. Carbon monoxide, nitrogen dioxide, sulfur dioxide, ozone, lead, and particulate matter. All of them will have limits, threshold that can be exceeded. Apart from it, there are benzene, that is a volatile organic compound, and benzo alpha purine, that is a polycyclic aromatic hydrocarbon, that is very important today because it's linked to the combustion of wood, pellets, and so on, biofuel. Okay, but we have more than 300,000 deaths. So a new directive proposal that was approved in the last November is trying to go near the limits of the directive, the political limits, with the scientific limits, with the WHO limit. But apart from it, they will monitor new parameters, essential parameters like ultrafine particles that are extremely dangerous because of the size, because they can penetrate, and black carbon that is part of, in some cases, these ultrafine particles, and is as a really interesting pollutant. But I think we have you have a specific talk about black carbon, so I'm not going to stop here. Ammonia or benzopyrene. Okay, and here we have these are the values, the threshold, or the limits, the limits of the directive here, and the limits of the World Health Organization by 2005. Going to the main pollutants, so here we have PM10, or especially PM2.5, that is 25 in the directive, in contrast with the 10 that are by the WHO. It means that, okay, it's more than twice. The same for PM10, and for ozone we have again an increase, and the NO2 NO2. There's a coincidence with NO2. Now we have a new guidelines, and then with a decrease in these values. So now, for example, the PM10 won't be 20 but 15, or PM2.5 not 10 but 5, or the NO2 will be 10 instead of 40. Wow, that's a huge decrease. And then this is the proposal, the approved proposal for the new directive that in case of, for example, in case of NO2, it's twice the new WHO value. The PM10 is 25% more. PM2.5 is double, and okay. So since the beginning, since the 1999, the idea was to look for the coincidence with the WHO values. However, after 25 years and with the proposal, there has been a new WHO guidelines, and anyway, we're going to exceed these limits. What's the problem? The problem is that thanks to this regulation, the evolution of emissions has been a decrease in the recent decades. We have seen this in the first slide, and then with these values, it was easy to go under these values. For example, here, look at your country. So, for example, here, I come from Spain. So, in Spain, okay, this is 75%. Only 5% of the air quality stations were exceeding. Probably in Madrid or Barcelona that have problems in some moments. But with the new directive, many of them won't be able to comply with this regulation. For example, in Spain, okay, more than 40% of the air quality station will exceed these limits. And in theory, this directive will have to, these values must be achieved by 2030. There has been there will be a delay because it was approved, but anyway, it should be. But anyway, will be over the WHO quality guidelines. And for example, here looking back, in Spain only 25%, 75% of the air quality station won't meet the requirement for PM10. Something similar happened with PM2.5, that been even more dangerous. Okay. Follow with Spain, but now Spain doesn't have PM2.5, but for example, Italy here, okay, so they are meeting all the requirements, but now they will be clearly, and the same by O2 concentration, okay? So, okay, that's important in order to ensure the quality of air we breathe and to decrease the number of deaths. Here we have, now these are our values, and we'll go into more or less these values, okay? And that more or less the same that other countries like Canada, California, or countries like Mexico. So we are going late. And then what will happen in the future? Because now we are living in a climate change scenario. So the first thing that will happen is that world population keeps growing, and more than 80% will live in cities by 2050. It's obvious that the urban places are, in terms of air quality, urban places are much worse than rural places. So most of the population will suffer or will live in places when the limits of the air pollution will be exceeded. So it means that air pollution will be a problem. So this is the London in 1952, when more than 4,000 people died due to air pollution. But this is Barcelona today. No big difference. And then in relation to climate change will affect air pollution. It's true that we are decreasing, and we have decreased a lot the emission of pollutants in the last decades, from NO2, particulate matter, or ozone. But it's also true that the climate change will increase at least two of them: the particulate matter and ozone, the most dangerous in terms of number of deaths. Okay, so well, NO2 is in the middle. So the projected increase in temperature and decrease in precipitation that is projected for Europe will increase the ozone formation because it's a secondary pollutant directly related with precursors and with radiation. The higher the radiation, the higher the temperature, the higher the production of ozone. At the same time, these conditions of lower rainfall, higher temperature, or more aerosols will increase the availability of fine particles and lower washing of the atmosphere, and there will be an increase in particulate matter due to two aspects at least. Wildfires, we are talking now, there is a discussion about we are in the Anthropocene or the Pyrocene. So in the future, there will be wildfires that will be unextinguishable, nearly unextinguishable. So they will emit a huge amount of particulate matter apart from destroying or to return to the atmosphere all the CO2 that has been sequestered previously, but it's not a subject today. And apart from it, there will be an increase in the Sahara-Sahel intrusions. So there will be an increase of ozone and particulate matter. So we have to compensate this increase with the decrease by controlling the emission in our cities. Apart from it, there will be an increase in atmospheric stagnation. The stagnation in the atmosphere is bad in terms of air quality because it breaks the turbulence in the atmosphere. This turbulence in the atmosphere allow the pollutants to be eliminated, to be removed. The stagnation means that the pollutants, they will be finally accumulated and then increasing the concentration that we breathe and increasing the frequency of pollution episodes in cities. And there will be also a lower wind intensity, less ventilation, and increasing greenhouse gases. Okay? Then, and the last problem will be, okay, there will be an increase of ozone, there will be an increase of wildfires, there will be an increase of Sahara-Sahel intrusions. That problem is that all of them can take place at the same time. Imagine in summer, there will be an increase of ozone because it depends on radiation, so the ozone concentration is always higher in summer. But at the same time, you have a wildfire that is typically occurs in summer, and the introduction of particulate matter from this intrusion. So there will be a strong increase in this specific moment, a strong increase of pollution. But apart from it, the question is that the pollutants are not alone, because the atmosphere is a huge reactor, a huge chemical reactor, and all these pollutants will react among each other or not, producing different pollutants or different compounds. Photochemical smog is only an example. But it's a typical situation that, for example, we have seen in Barcelona. This aspect, like fog, is not fog, it's pollution. And this pollution comes from these photochemical smoke processes. And then these photochemical smoke processes that take place in areas with heavy traffic, sunlight, and mountainous terrain, that's why these cities are perfect for it, needs precursors, heavy traffic that is emitting carbon monoxide, volatile organic compounds, and nitrogen oxides. At the same time, we have warm weather and high radiation. So there are reactions between these elements and oxygen that is very reactive, the oxygen atmosphere. And then when we have a slow movement or air masses, it means when we have increase in the stagnation of the atmosphere, there will be a net accumulation of these pollutants. Okay, and then that's why we have a problem, because we cannot think only in one specific element and a specific component, but in many of them at the same time. Okay, I don't know if I have more time or yeah. Okay, but because I have the idea was to explain why we have this process of smog, and this term, for example, we need nitrogen oxides and volatile organic compounds, because the idea is, okay, if you're able to decrease the precursor, decrease NO2, for example, there will be a decrease in ozone. That is the main result of this process. But it's not true, because in some cases, the volatile organic compounds that are the hydrocarbons that comes from the combustion processes can also be emitted by forests, for example. They are natural volatile organic compounds, but anyway, they can react with oxygen-derived forms to give this problem that is ozone and all the oxidizing compounds like peroxy acid nitrates and many others. And then that's the process in a day. We have emissions, a peak of emission due to traffic when we go to commuting to the work, or we go to the schools with the children, and then there are emissions of these primary pollutants as NO, and then it immediately starts to and part of NO2, and then it immediately starts to react to give NO2, and from this NO2 and with light, there will be a production of ozone that is here. The maximum peak is here, just in the opposite, in opposition to the primary pollutants. But in the middle, there will be the production of aldehydes, and at the end of the day, there will be the production of many other oxidizing compounds. But at the same time, there will be other processes linked, for example, to acid rain. This part of this NO2 will react with water to give nitric acid, or sulfuric acid, or sulfates, or particles. In such a way that at the end, and then there will be reactions between these compounds, this particulate matter, and these gases to give nitrate particulate matter, or other organic compounds, nitrate organic compounds that are extremely toxic. And the same with sulfurous smog. It's not so common today because we don't burn coal in cities, but it was the explanation for this more than 4,000 deaths in London, and it comes from sulfur, for example. Sulfur, that when this is burned, the burning is an oxidation process, so it emits SO2 that will react to give sulfuric acid. So there will be a acid fog with plenty of particles and that will affect giving things like this. Okay, we have an emission of this in winter. They are cooling, they are burning coal, but here there is a stagnation due to a thermal inversion, for example, and then instead of removing, all these compounds are accumulated, and that's why in these 4 years there is a huge increase in the concentration of smoke that is directly related to SO2 and with the number of deaths. Okay, well, that's a problem. So we cannot control the atmosphere. There's an stagnation or not. So we need to control the thermal inversion. Okay, that's all from my side. Okay?